Hello guys, welcome back to another episode of this stuff. Today we're going to be sketching two titration curves from scratch. We're going to be sketching two titration curves from scratch: a strong base, strong acid titration curve, and a strong base, weak acid titration curve. So, for the first one, pause the video now if you want to try it, and if you're ready, we'll do the work solution now. Alright, so in order to sketch a titration curve, I look for either 3 or 4 points, depending on what is being titrated with what. If it's strong acid, strong base, I look for 3 points: the initial pH before you add the initial pH, the pH at the equivalence point and its corresponding volume, and it's the limit as the volume of base goes to infinity. So the first thing I would like to do is draw out some axes here. And the first thing I want to do is get these. So here's 2, 4, 6, 8, 10, 12, and then 14. 14 there, and then oops, sorry, I'm just changing my seat position here. And then in order to get the volume, the x-axis, the labels on the x-axis, what I try to do is first I consider how much volume will it actually take to neutralize. So I know that, so the reaction is HCl plus NaOH yields ACl plus H2O before, after. And I know that there's 25 mil of 0.113, and I know there's 36.03, 0.103 molar, which yields back here, click the back arrow here, mole, and then mole. Let's just quickly calculate how many moles there are. 25. 0.00285 moles for that, and then so 0.0037 moles. This is the limiting, so I'm going to put a little L there, 0, and then at the equivalence point, the pH is 7. So now I just need to find how much volume that would take to get 0.0285 moles. So now let's quickly do that. Let me move my scrap work somewhere like that's not on the actual graph itself. So here's sort of my rough work that I would do. So first I'm calculating the pH of the equivalence point, simply because I want to get an idea of how far I need to label my x-axis. So I know that I need, so there's 0.00285, 0.00285, so 285 moles EQ point at the equivalence point. So now I just need to find the volume, which is 285 divided by the concentration, which is 103, which yields me 27 milliliters at the equivalence point. So I think if we go on our axis in terms of fives, so 5, 10, 15, 15, 20, 25, 30, 35, 40. So 5, 10, 15, 20, 25, 30, 35, 40. And having done the calculation of what volume of NaOH I need at that concentration, I get that I need 0.0276 liters or 27.6 mils. So I know it at pH of 7, which I'm going to just use a dotted line to mark. Here's about 27 and a half, so I'm going to just, that is my first point I'm going to mark. The second point is the initial pH, which is just the pH of the solution before we add anything to it. And this is a pretty easy calculation. It's just minus log of the H plus concentration, which in this case, since it's a monoprotic strong acid, is just the concentration of the acid, 0.113, which yields me a pH of about 0.94. So we call that 1, slightly below 1. Let's call it there. And then finally, the pH as we go to infinity, or the final pH, which we assume that there's no acid there. We just take the limit as it goes to infinity. So that's just the pH of the base. So 14 minus negative log of 0.103, which gives me a pH of 13. Okay, I just needed to make sure where my dot was, which gives me a final pH of about 13. So I'm going to just sort of do like that. And then remember your general shape of a pH curve, that it generally doesn't tend to get sharp in terms of increase. So lastly, when we sketch the curve, we get something like, we'd get something like that. It's just ever so increasing. And then here we get a sharp increase. And then we sort of level off there. And that's sort of what our pH curve would look like. So what I did, in essence, was I plotted 3 points that I need to know, the before, the equivalence point, and the afterward. And for the equivalence point, I calculated how much volume of base do I need to reach the equivalence point. For the initial pH, I just calculated the initial pH of the solution, sort of like you would any other sort of pH problem as we did in the last video. And then for the final pH, I assumed that I made the assumption that there was negligible acids present in the final solution as we go to an infinite volume of base. And then I just took the pH of the base solution there. And once I plotted those points, I just connected them using the general shape of the pH curve for strong acid, strong base that you should be familiar with. So you only needed the 3 points. Alternatively, you could get multiple points and sample along the way to get a pH curve as well, and you would do that by calculating the net H plus concentration over and over again, but you only needed the 3 points. So that's sort of what the strong base looks like. Now let me switch over to this page. Pause the video now if you want to try the highlighted question, and just wait 2 minutes for the worked solution for that highlighted question. Alright, presumably you're back, so let's switch over to the other screen. So for this pH curve, we want 4 points. 4 points. 1, initial pH, 2, pH at half EQ point, because this is strong acid, weak base. Now this is weak acid, strong base titration, so we want 4 points. And the same sort of situation for weak base, strong acid titration, except there would be a slight difference in the curve, which I will draw out later. 3 pH at EQ point at the equivalence point, and then 4 pH at infinity. So those are our 4 points we want to take. So if I just now let's first draw our graph. So 2, 4, 6, 8, 10, 12, 14, 2, 4, 6, 8, 10, 12, 14, VB, mil, pH, and then the first thing I like to do is first I like to get deal with the equivalence point, because that's generally the most variable. So we know we had 25 mils of HCN. So in order to deal with the equivalence point, I'd first like to consider the reaction we're doing. So NaOH plus HCN yields NaCN plus H2O. Before, after. Now this one is going to be a little bit more involved, since we have to calculate the pH of the equivalence point too, which I'll show you what to do there. But this is a culmination of many skills. So we know that we have 25 mil at 1 molar. So from that information, I'm just going to do that math in my head. Since we're told in the question there's 25 mils of the acid at a concentration of 1 molar, we know that there's 0.025 moles of the acid. So 0.025 mole, and then I know that there's 0.025 mole of the salt, which we want to consider the pH of. And the reason the way I did that is I just took the mole ratio, it's 1 to 1, and then 0. Remember to get so now that we have the amount of moles at the equivalence point we want, so we can rearrange N equals CV for the volume. So moles over concentration gives us the volume, and we have 1 molar NaOH. So once you know it, our life is made easy. So 0.025 equals 1 times V. V equals 0.025 liters, or 25 mils. So now I'm going to label my x-axis 5, 10, 15, 20, 25, 30, 35, 40, dot, 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 dot. So 5, 10, 15, 20, 25, 30, 35, 40, and so on and so forth. So now that I know the volume at the equivalence point, unlike the strong acid, strong base one, where we automatically know it's 7, now we have to consider the fact that this salt solution that is created can affect the pH. And we know the Ka value of the acid, and we know that Ka times Kb of the conjugate base equals to Kw. So we need to get Kb, and then we can just really treat it like a pH of a weak base, which is much easier to do. So let's calculate that first. So 1e negative 14 divided by 6.2 times 10 to the negative 10, which yields us a Kb value of which yields us a Kb equals 1.6 times 10 to the negative 5. I just substituted in the value for K that we got in the question, and then I know what Kw is off the top of my head, 1.0 times 10 to the negative 14, and then now we can just draw sort of an ice chart. So we know that Cn minus yields is in equilibrium with H plus. We know that the following equilibrium is true. HCN Cn minus. We know that the following equilibrium is true, and we know the concentration of, well, we know the concentration of this is 0, but we need to treat it like a weak base, so we know that Kb equals BH plus over we know that Kb is that, so we can get the pH pretty easily by just doing an ice chart where, and we know the concentration of the Cn minus, so we know that Cn minus H plus is in equilibrium with HCN, and we know that Kb equals Cn minus over H plus and HCN, which we know is 0, but for all intents and purposes we're just going to treat it like it's a constant since it's just a Kb, so we just know it's x squared over the concentration of Cn minus x. We know that Kb is just that. It's just the conjugate acid. The conjugate acid of it. We know it's that, which warrants that. We're just going to call the change x. And we know the concentration of Cn is... Note that because we added 25 mils to our final solution, it's double the volume, so it's 0.025 mole over 50 mil. So we get that Kb equals x squared over 0.5 minus x, so 1.6 times 10 to the negative 4 equals x squared over 0.5 minus x. And if you're wondering where I got the 0.5 from, it's from that 0.25 mole of NaCN over 50 mils total. B plus VA. I apologize if my work is messy, but yeah, I apologize. We're just going to store this value of x to this waypoint, to this value here. And now I'm going to use a program called Solver on TI-84 to solve my equation. Oh, fuck. Sorry guys for the long video, so we'll just solve it. So we get that x equals 0.0028, and then we know that since this will yield, this to the negative log would yield us a POH, we just do 14 minus negative log x, which yields us an answer of negative 14 subtract negative log x, which yields us a pH of 11.45. I know that was a lot of work to literally get one data point, but we have it now, so let's mark it on our graph. I promise you the next three are quite a lot simpler. Bye-bye. So now we have our first data point, which is 25 mils, and 11.45. So I'm going to just sort of draw a dotted line to where I would guesstimate 11.45 is, and mark it with our Memes paintbrush. And then I promise you the next couple of data points are easier. Now, since we know at half equivalence point we have a buffer solution, so at half equivalence point we know that the pKa equals the pH from just our general titration curve. And if you wanted to do a derivation of that, there's probably a derivation on the buffers video as to where the buffers video as to why pKa equals pH. But so now the second point we're going to get is the half equivalence point, which, since we know that Ka equals H plus concentration at the half equivalence point, we're just going to do negative log of Ka, so 0.2 e negative 10 to get the pH at half equivalence point, which is about 9.2. So negative log Ka equals about 9.2. So 9.2 is about here, let's say. Our initial pH. Our initial pH is just an ice chart. So let's do the ice chart. This is a bit of an easier ice chart to do than the last one. It's just H plus Cn minus over HCN. And we know that would just yield to, if we call the change x squared over 1 minus x. So using our graphing calculator, we can get our value. Using our graphing calculator, we can get the value for x, and we get that it is about 2 x equals about, so x equals 2.48 times 10 to the negative 5, and if we take the negative log of that, we get that our initial pH is about 4.6, so about there, let's say. And then lastly, our final pH, the pH as we go to infinity, is just the pH of the base, which this thankfully is a much easier calculation. It's just 14 minus the negative log of the base concentration, which is just 1, so that's just 14. So if I draw an asymptote at 14, and now that we have all our data points, let's connect them, and we know that the shape of a weak acid titration curve has a bit of a jump initially, and then sort of we cross the half equivalence point, and then there's a sharp sort of increase. Ooh, that's not good. Let's do a different one. So there's sort of a sharper increase, and then something sort of like that. That's sort of what the curve should look like. It doesn't fit the full data points correctly. That's